are different operations that we can execute on processes. We can create them, we can terminate them, and we can allow them to communicate and cooperate as well. So a parent process can create some child processes for multiple reasons. Let's say we have a very large program that will need a long time to be executed, and one process alone will take longer. So that process is allowed to create some child processes to break down the task into smaller ones that can be executed in parallel, so we can speed up the process and accelerate and gain some performance benefits. So remember that every process has a unique identifier called a PID. Again, it is saved on the PCB of that process. So when a parent creates a child, there are multiple options there. It's up to the programmer to choose what type of resource sharing they want them to have. They can either share all resources, so the parent can share all its resources with the child, or they can just have a subset of resources or no resources at all, right? So let's say I have a very large array that I have to, so I have a very big table right here, and I want to execute a summation of this table. So I'm going to create this is the parent, so I'm going to create two child processes. So child 1 will operate on this left half, and child 2 will operate on the second half of the table. So I could decide to simply share this subset of the table with child 1 and the other subset of the table with child 2. And so on. So it depends on the application. You get to choose the amount of sharing that's happening between parent and child. By default, there is no sharing of resources at all between these two processes, and they're completely independent standalone processes. In terms of execution, you get to choose also if you want them to execute concurrently, so they continue to execute at the same time, or if you want the parent to hold the execution and wait for the children processes to finish first, then they send their results to the parent, then the parent continues execution. So again, it depends on the application, what the program wants, and what the developer wants to do. This is an example of a tree of processes in Linux. It shows the main root, which is the systemd, and then we can see some child processes there, like the sshd, or we can have the login, and then we can see here a new user has logged in and is currently using bash. It is executing some Linux commands like a text editor and so on. So each of these gets its own standalone process with its own unique PID. So how does the process creation process happen? So it is initially, so we have the parent that calls for a process creation. Under Linux, we do that using the fork system call. Remember, we talked about system calls, right? So we said it is an interface to operating system services. Whenever we request an operating system service, we do that using system calls. So now a parent is calling for the service of creating a new process. So it will do so using the fork system call. So initially, the created child is a duplicate of the parent, meaning it has exactly the same code of the parent, right? So let's see how does this happen. So we have a parent here that calls the fork system call. So the fork returns two things. It returns the new child's PID to the parent, right? Let's say the fork has created a child with a PID Let me choose this one. It has created a child with PR. No, this one. 1000. This is too big. 1000. This is the PID of the new child, and this is what the fork system call returns to the parent. Now for the child, it returns 0, simply number 0 to indicate the successful execution of this system call. Okay, so you can use the exec system call to ask the child to execute any command that you want, or you can discard this part and simply provide a file that you want the child process to execute, like a .c file or a Python code, or any or simply provide the lines of code directly to the child process to execute. So once the child finishes execution, at the end, you want to call the exit system call. This allows the child to signal the parent that it is finished execution once it's done. And then if the parent is currently waiting for the child to finish using the wait system call, then it gets signaled that the child is done and the parent may continue execution. So if you want the parent to not make any progress until the child is done, so you have to use the wait system call in your code. This makes the parent process hold and do not make any progress until the child is signaling its termination. So this is a simple description of the create a new process function. It contains multiple steps. Obviously, the allocation of a new PCB is one of them. And then you can see here that it is indicating that the parent of this newly created child is the calling parent, right, self, and it is adding this newly created child into the list of children of that calling process, right? So remember, this is a linked list. So here we can list the different children created by that process to keep track of the tree. So this is an example of a C program that does this forking operation or creating a new process. So here, this is our main parent, right? So here we can initialize a PID of type PIDT to simply save the process identifier. This is an optional step. You can skip it if you want. So then the parent here is calling for the fork system call. And as we said, the fork will return two things. So here you can test for any errors. And right here, you can test for the value of the return of the fork system call. So we said to the child, it returns 0. So this is how you know that this is the child space. So right here, you can write any lines of code that you want the child to execute, like printf hello from child, or make it execute a mathematical operation, or anything that you would like this child to execute. So here we are simply asking it to execute the ls command, which simply lists the different files in the current directory. And then right here, the else here, which means if the return value of the fork system call is positive, then we know that this is the parent space. So here you can do things like the wait system call, as we said. So here you are asking the parent to hold execution until the child is done, or you can simply add a simple printf statement saying that the child is complete right after the wait system call. So if you have multiple fork system calls in your script that are stacked one after the other, you have to be careful here into about the number of processes that you are creating, right? So the number of processes will be 2 of n, where n is the number of forks that you have stacked, right? So if you stack 3 forks here, one after the other, without the if else statement that we saw before, then you end up creating 8 total processes. So how did we end up with 8? Let's see. So initially we only have the parent, right? So we said we have 3 forks, right? The first one, second one, and the last one. So initially we only had the parent, then the first fork happens. So this will make parent P0 create child P1. So right now you have 2 processes, P0 and P1. If you do not do the if else statement, if you do not specify which process is asked to create a new process, and you just entered a second fork right here, then what will happen is that both the current processes will continue executing the lines of code that comes after that, meaning both of them will execute this fork system call. So this will result in P0 creating another child, which is P2, and P1 creating its own child, which is P3. Again, all of the current existing processes will continue what comes after, which is a third fork. So all of the currently existing processes will create their own processes, child processes. So P0 will create its own, which is P4. P2 will create its own, which is P5. P1 will create its own, which is P6. And P3 will create its own, which is P7. So be mindful of where you are placing the fork, and make sure you use the if else statement to make the differentiation between the different spaces, the child versus the parent. Obviously, if we can create a process, then we can terminate it. So the exit system call causes the termination of the process and the deletion of that process. Also, we talked about the wait system call, which make the calling process hold until its child finishes execution. We can force a process to terminate, and obviously there are multiple reasons why you would want to do that. So to do so, you can use the abort system call. So here, let's say we have this parent process that has multiple users, child processes, and each user has its own processes, right, that it has created. Let's say that user 3 has suddenly, not suddenly, I mean decided to log off. Then there are multiple options. Either the grandparent becomes the new parent of the processes that have remained with no parent after that user has logged off, or what is currently common in Linux is to completely destroy all the hierarchy, all the different children of a process once that process is terminated, and we call that cascading termination. That's what's really common in operating systems. So there are 2 types of processes in the context of child-parent relationship. We have zombies and we have orphan processes. So with a zombie process, so let's say a parent created a child, right? And let's say the parent forgot or did not call the waiting system call, then once the child has finished execution, it won't find the parent to report its termination status to, because there is no wait system call. So we call that a zombie process. On the other hand, let's say a parent created a child and then it did not again use the wait system call and it completely terminated. It's not in the system anymore. Again, the child will not find a parent to report to, and the parent is already not in the system, and we call that an orphan child process. So this is a simple explanation of the destroy function. Obviously, we have to deallocate the different linked lists and close the different open files, deallocate resources, and at the end deallocate and destroy the PCB.